Yes, good morning to everyone. So in the previous class, we have seen about some of the basic concepts which are related to the energy bands, which is one of the most important topics because the energy bands cover most of the valence as well as intrinsic as well as extrinsic semiconductor bands. That means what I have said you in the previous class is it will cover both the points where antibonding as well as bonding recordings are present. So that is followed by an important topic today, and in gate at least 2 to 3 questions will be asked in this energy bands, that is covering both intrinsic as well as extrinsic silicon as well as semiconductor part. So why mostly silicons are used in this particular energy band is it is because of the value which is present inside it. Let us take for an example, silicon is going to cover a zero point 0.8 electron volts. Within that 0.8 electron volts, a group 4 material will be located. In most of the cases, this group 4 material will be used as a vital element for the semiconductor. That is the reason why energy bands and Fermi level concentration plays an important role in silicon based semiconductors. So that's what we are going to see in today's class. Again, I repeat it. We are going to see about the most important topic, energy bands in intrinsic and extrinsic silicon. In this, we will discuss about two different things. One is the basic definition, what is called intrinsic and extrinsic semiconductor silicon bands, as well as we will discuss about what is the maximum energy band that needs to be covered for free electrons as well as holes, what is a lower energy band that will be covered for free electrons as well as holes. That we will see it first, then after that we will move to the solved gate problems that is present in the previous question paper, as well as I will also discuss some of the questions which are related to the gate point of view for both intrinsic as well as extrinsic silicon semiconductors. Now we will move to the next slide here. So first, let us see about what is the electrical properties of insulators and good conductors. See, most of the insulators and good conductors will be having two different materials. One is called germanium and the other one is called silicon. Both this germanium as well as in silicon, two different energy bands will be defined. So that's what I have given here. It will be in the order of 1 electron volt. This 1 electron volt is observed as the energy band separation between the intrinsic as well as extrinsic semiconductor. This is very important because all the questions in the gate will be based on this energy band. They will give you, let us take for an example, I will show you the question later. Before proceeding to the question, in the first sentence itself, they will give you one word. Consider the energy gap between the source and the destination. That means the energy gap between the silicon as well as germanium or between the holes and electrons to be 1 electron volt. So in this case, what we are going to do, we are going to directly define the variable which is called as EB. Usually this energy band will be represented in terms of EB, and always remember the order of 1 electron volt will be the narrow energy gap that is represented between two different electrons as well as holes. This is the first point which we have to remember in the semiconductors. Either it may be germanium, either it may be silicon, it is not at all a problem, but always they will follow two different things. One is called electrons and the other one is called as holes. In these two different things, we will be having one electron holes as the major separating bands between two different processes. So remember this, students. Then after that, you can see this distinguishing marks where the semiconductors are differentiated into two different types. One is called intrinsic and the other one is called as extrinsic semiconductors. You can see there the other word for intrinsic semiconductor is pure semiconductor, whereas the other word for extrinsic semiconductor is impure semiconductor. That's why extrinsic semiconductor or impure semiconductor is again differentiated into two different types, or we can say it as two different bands, N type as well as P type bands. So usually this is represented by electrons as well as holes. So now let us move to the next slide. So you can see here, this is the schematic representation of how the electrons and how the holes are moving and how the bonds are created and how the electrons and holes are being unbonded with respect to each other. So you can see this diagram there. There in your left side, pure semiconductor, which is called as intrinsic semiconductor, is expressed here. There we are having four different pair of electrons with four different pair of holes. What is happening in this case in intrinsic semiconductor is all the electrons and all the holes are attracted with respect to each other. That's what they have represented in pure semiconductor based. No holes and no electrons are being unbonded with respect to each other. You can see there. I have here it is represented by +4. That means 4 electrons are there, 4 holes are there. All are bonded with respect to each other. But you can see through the right hand side diagram where the impure semiconductor, which is called as extrinsic semiconductor, even it may be germanium or it may be silicon. The basic thing here it is both N type and P type stands unbonded with respect to each other. As I have already told you, unbonded represents all electrons and all holes will not be combined with each other. You can see here, you can see the schematic representation. See here, 4 different electrons are present here, but see here, 5 different holes are present here. Only 4 different electrons and 4 different holes are bonded with respect to each other, but the extra additional hole remains unbonded. That's why it is called as impure silicon. Now, what is our target achievement is, first we have to check the energy gap here. As I have already told you, the energy gap that is represented in terms of upper level as well as in lower level between the electrons and holes should be exactly equal to 1 electron volt. That's what we have discussed in the previous slide, right? So 1 electron volt is the separating distance between the electrons and holes. So that's what here also they are saying. Suppose if a hole and an electron remains unbonded with respect to each other, first check the energy band. Then after that, see through the another constraints that are represented in all the conventional problems. You can see through N type and at the similar type and at a similar time compare the P type representation also. See here, 4 different types of electrons are present here, but you can see there only 3 holes are present here. Since due to lack of holes, 1 electron remains unbonded with respect to holes. But in N type, I have represented here as +5. That means 1 hole cannot able to get bond with the corresponding electron. But in P type, I have reduced the number of holes and it is very clear that the number of holes cannot able to get bond with respect to each other. There will be some confusion in my words. So I repeat it again, understand clearly. +5 represents the number of holes here. +4 represents the number of electrons here. Here in N type, the electrons remains unbonded with respect to holes. Again, I repeat, the electrons remains unbonded with respect to holes. But you can see through the p type there, +3 represents the holes, +4 represents the number of electrons. So automatically it is clearly indicated that one hole remains unpaired with the number of electrons here. So one hole cannot able to bond with the remaining electrons that is present in p type. The major thing what we have to see here is all the electrons and all the holes should be bonded with respect to each other. That is called as free movement of electrons and holes. Usually in the basic, that means in electronics and devices, you might have seen various different things. We will start usually with electrons and holes combinations only. Usually the electrons and holes should always move freely with respect to each other. If they are not moving freely with respect to each other, automatically a unbonded situation is going to rise, and as a result of this, the electrons or the holes will remain in unsaturated condition. We have to avoid this particular unsaturated condition here, because if the electrons as well as holes goes to a particular unsaturated condition, then it is very difficult for a particular element like germanium or silicon to be combined with each other, and the working functionality of silicon, which is expressed in terms of energy band as 1 electron volt, will not be satisfied, and it cannot be used under any real-time implementation process. That is the main drawback here. That's why again and again I'm telling we should check the free movement of electrons. That is our second constraint. First constraint is our energy band, EB is equal to 1 electron volt. Second constraint is we have to check whether free movement of electrons and holes are present or not. If free movement of electrons and holes are not present, then we cannot able to apply silicon as one particular point in all real-time cases that are present in the industries. So be careful about it. Check the free movement of electrons. Then in intrinsic semiconductor, mostly silicon and germanium one will be used, as I've already told you. So let us take for an example an energy gap. Suppose if the energy gap is less than 1 electron volt, what we are going to do? That's what we are going to discuss in the next point. Okay, I have said you two constraints. Follow 1 electron volt because that is the minimum energy band separation between the electrons and holes. Suppose if you are not achieving the target, suppose if your energy band goes below 1 electron volt, what you are going to do? What you are going to do means you have to check how many electrons are present. You can see through the third point here, how many electrons are present in that particular point, you have to check it. Then after that, where the energy gap is missing, that you have to check between two different bands. Those two different bands are called as valence bands and conduction bands. This valence band and conduction band will be again represented by using the terms which are called as anti-bonding as well as bonding. Here the valence band is usually called as bonding and the conduction band is usually called as anti-bonding materials. So first check the energy gap for the electrons, how many electrons are present, whether all the electrons is having sufficient energy to join the valence as well as conduction bands. So I will explain you with the previous diagram itself. You can see here how many electrons are present here. 4 different electrons are present here. First itself I have told you, you have to check how many number of electrons are here. So the number of electrons EV is equal to 4. Now check for all the 4 electrons whether they are having the corresponding energy level or not. All should have the energy band which is almost equal to 1 electron volt. every time EV should be always equal to 1 electron volt. That's what you are going to check in the pure semiconductor. Suppose if you observe that the energy band between the electrons is very much lesser, then automatically the silicon or the germanium material will remain in the valence band. It won't go to the conduction band because there is no bonding represented here. That's why it is automatically going to the valence band. It won't go to the conduction band. Then after that, intrinsic semiconductor is having a specific definition here. That also I have represented here. You can see there. Here, the intrinsic semiconductor will be defined where the number of conduction electrons is equal to the number of holes. That's what I have already told you. Number of electrons must be equal to number of holes in pure semiconductor. That's what they have given in this definition. So I think you are clear about the intrinsic semiconductor now. Remember just two different points. Energy band is equal to 1 electron volt. If the energy band is not equal to 1 electron volt, check how many electrons are present. If the number of electrons are present and if the energy band constraint is satisfied, leave it. Otherwise, the electrons will automatically shift to the valence band, and therefore as a result, you should check whether the electrons and holes are equal. So next, we will see this conduction band as well as valence band. Now here, one important energy level will be defined. Suppose if you are not having the particular energy band, I have already told you the electron will occupy the valence band. It won't go to the conduction band. That's what they have given here. That is called as Fermi level. Okay. Suppose if you are not having corresponding energy gap to move from one particular point of view to another particular point of view. That means from electrons to holes, if they are not bonding with respect to each other, and if the energy level goes below a particular 1 electron volt, then automatically the electrons will shift to the valence band. That is called as Fermi level. And the value for this valence band is equal to 0k whenever Fermi energy is present, and Fermi energy will be defined by using the variable which is called as EF. Whereas already I have told you the energy level, the minimum energy level will be defined by using 1 electron volt, which is equal to EV. Okay, E underscore V. But here it is E underscore F. E underscore F is always called as Fermi level, and the value is equal to 0k. I again repeat the process why we are going to the Fermi level. Suppose if number of electrons cannot able to pair with number of holes, then automatically all the electrons will be shifted to the valence band, and that is called as Fermi energy, which is represented by EF. So you can see there in this diagram which I have represented here, the Fermi level lies between conduction as well as valence band. Okay, so now let us move to the next point. So here it will be very clear. So you can see here the energy gap I have represented here. EF, Fermi level, will stand at the midpoint between EG as well as EG by 2. You can see through the right hand side graph representation here. I have taken the minimum value as 1 and minimum value as 0 and the maximum value as 1. In between, if you are having the Fermi level concentration, which is denoted by EG, it is always equal to 0.5 electron volts. So this is your second constraint that you need to remember. If you are not having energy level which is equal to 1 electron volt, check for all electrons, go to the Fermi level, complete it, check whether all the electrons and holes are matching again. This is your constraint which you need to check here. Okay, so now, so these are all the important derivations that we need to remember for solving a particular problem that is represented in gate question papers. Okay, so see here, we are having the temperature greater than 0k, because the minimum temperature for satisfying the Fermi level energy gap is 0k, So always the temperature should be greater than 0K, and the probability expansion, which is given by P of E, the expectation of probability for this particular temperature in the Fermi level is 1 divided by 1 plus E power E minus EF divided by K into T. Okay, T represents the temperature. We all know about EF. It is nothing but the Fermi level. E represents the minimum energy level, 1 electron volts. Then if they have given all these values, you can solve, you can use the constant K, which I have told you in the previous class. Then you can solve this particular problem. This is your first mathematical equation for solving a basic level problems in a gate. Okay, I repeat again, the expectation of probability P of E is given by the formula 1 divided by 1 plus E power E minus EF. E means 1 electron volts. 1 minus what is the Fermi energy that you have observed when the electrons is not paired with particular hole, that you have to represent that value divided by K into T. And another thing, suppose if they have not given you the value of E, or if they have, if you can't able to observe the value of EF, what you can do is you can directly solve E minus EF by using the equation that I have represented in the right hand side, which is equal to Eg divided by 2. I repeat again, if in question paper, observe the question clearly. Suppose if they have not given the value of E as well as EF directly, you should solve E minus EF by using the formula which is equal to Eg by 2. Where this Eg by 2 I have represented, you can see here. Eg by 2. There, here I have represented. The above green box represents your conduction band. You can see here, this is the schematic diagram that I have represented here as the line diagram. Okay, so this is your conduction band in the green color, and this brown color represents your valence band, and in between this you are having your Fermi level energy gap. And if you are observing the Fermi level energy gap in terms of 0.5, that is given by Eg divided by 2. Okay, so that's what they have represented here also. E minus EF is equal to Eg by 2. So remember this formula. Next, see, our main important theme here is, second thing you have to observe your question paper. Okay, E minus EF. Now you are observing by using the formula Eg by 2. Okay. Next thing, they will confuse you by using the term as germanium as well as silicon. Now what you can do is, suppose if they have given the word as silicon, you can directly take the value as 0.55 electron volts in place of E minus EF. I repeat again, understand clearly. Either it may be direct problem or either it may be indirect problem. Don't worry about that. First see through the question paper. First you have to observe what is the value of E, what is the value of EF. I will show you the sample question paper here. We will observe that once. So you can see here. Just we will see here. So see here, assume silicon band gap 1.12 electron volt. See here, they have given the band gap clearly. EB or EG, they have given directly here. So there is no need for you to search anything. Directly you can apply the probability formula here. So that's what they have represented here. 1 divided by 1 plus E power E minus EF divided by KB into T. Directly they have solved this problem. But suppose if they have not given this EB, then you have to check what material they have given. Okay, material in the sense either it may be germanium or either it may be silicon. So first we will see for silicon here. So you can see here the silicon, you can directly solve the value of E minus EF by using the formula Eg by 2, and the value for Eg by 2 for silicon, only for silicon. See students, you will face the confusion in question paper. Most of the students can't able to get the right answer which is relevant to all the options is because they cannot, they won't observe what is the material they have given. Just like that they will substitute the value. They won't observe what is the energy level given directly, eg by 2, eg by 2 directly they will get the answer, and they will substitute there also. The question paper setter, he will give you the option also. Suppose let us take for an example, you are getting the value for Eg by 2, and even with the representation of silicon, you are getting the value as 0.5. That option also will be there, but the original answer will be equal to 1. How? Because the value of silicon is already equal to 0.55 electron volts. You won't substitute that particular value. Automatically you will see the value, directly you will substitute it. There also the wrong answer will be represented. So be clear about the question, what type of material they are providing you. Either it is silicon or either it is germanium. Observe it very, very clearly. And next thing what you have to check is temperature. See here, again I will show you the question paper here. See here, they have given the room temperature clearly. You can able to see what is the room temperature they have given here. 300 Kelvin they have given. Okay, now you are given a freedom to substitute the value of temperature directly. You are going to substitute the value of kb, it is a constant, you are going to substitute it directly. Okay, but in some cases they won't give you the value of temperature, they won't give you the value of k. What you have to do is you have to again check whether it is germanium or silicon. In most of the cases silicon will be represented, germanium most of the cases we will leave it, because silicon is the most famous material that we are using. So therefore the temperature multiplied by the constant value will be equal to 0.026 electron volts. So with these two different values you can directly solve the problem. Now you can see that if they have given you silicon 1 divided by 1 plus e power 0.55 divided by 0.026, you can substitute it directly. There you will get your answer. So this is how a basic problem can be solved in intrinsic semiconductor using silicon material. Okay, so remember this formula. We have started with the probability of expansion P of E. The expected probability is equal to 1 divided by 1 plus e power e minus ef divided by k into t. Suppose if they have given all the values directly, if they have given the energy level as 1 point something 1 electron volt or 1.12 electron volt, take it directly. But be clear what is EF, what is E, what is K, and what is T. If they have given directly, substitute it by using the expectation probability formula. If they have not given it, observe the question paper, either it is silicon or it is germanium. If it is silicon, directly substitute this value for E minus EF for 0.55 electron volts. Suppose if they have not given you any material, directly you solve by using the formula Eg by 2. After that, for silicon, the constant multiplied by the temperature, room temperature 300 K is equal to 0.026 electron volts. Divide it in the expansion formula, then you will get your answer. I think you will be clear about this particular point of view. Next, we will see what happens if the denominator, that means if the unity in the denominator is getting ignored. Okay, suppose if you are getting the value greater than 1, what we are going to do means we are having the next probability of expectation. The expectation of probability will be given by the formula e power minus eg divided by 2 kt. This is applicable only for the case when the expected probability in the first constraint, which I have told you by using the formula 1 divided by 1 plus e power e minus ef divided by kt is greater than 1. In this case, you have to go to the next probability of expectation, which is given by e power minus eg divided by 2kt. Next, if you are solving the problem by using the number of electrons that is available at the top position, then you can use this particular formula here. So I think you can able to see the formula here now. You can see here n represents the number of electrons available at the top of the valence band. Already I have told you, if the electrons and if the holes are not bonded with respect to each other, it will remain in an unsaturated condition. Therefore, here n plays an important role. So n represents the number of electrons that is already available at the top of the valence band. So I will show you the diagram again. So you can see here, you can see through this diagram. Here the electrons and the pairs are not matched with respect to each other. Automatically, some electrons are present in the Fermi level energy gap between the conduction band as well as valence band. Okay, so that's what they have represented by using this formula. So Ne represents the number of electrons that is promoted across two different gaps between the valence band as well as conduction band. So Ne is equal to n into e power minus Eg divided by 2kt. Okay, so now let us move to the next thing. See, one of the important thing you have to remember is this tabular column. What is the value for electrons in term of silicon? What is the value of electrons in terms of germanium as well as for holes? See here, check this table. Okay, check this table for electrons. The mobility value at room temperature, RT represents your room temperature. The mobility value, which is indicated by the units meter square or V or S, can be defined by using the values of 0.14 and 0.39 for electrons. For holes, it is defined by the values 0.05 as well as 0.19. Why I am giving you this particular value is, you can see through your left hand side, I have given you one formula for solving the mobility. So in your question paper, in your gate question paper, nearly many times whenever they are asking the question about intrinsic semiconductor, they will either tell you to provide the answer by using this probability of expectation values by using these three different formulas, or else they will ask you the question related to mobility. So you can see here, whenever they ask you about the mobility concept, you have to remember about two different wordings. One is called a drift velocity and the other one is called as field gradient. These two things you should remember it, because without drift velocity meter per second or volts per meter field gradient, you cannot able to solve the mobility problem. So therefore, you can see here the formula for mobility will be given by sigma is equal to Ne into E into mu E plus number of holes NH into the electrons number of energy level that is present in the particular holes, then after that, which is multiplied by mu h. So this is the thing which you have to remember in case of mobility for an conduction that is present in intrinsic semiconductor. I repeat the formula again. Sigma is equal to Ne, number of electrons, into the number of energy gap that is present in the electrons into mu e plus number of holes. You have to count the number of holes first. That's what I have told you in the first diagram itself. I will show you the diagram again. See here, this is what I have told you previously. Here the number of electrons is 4 for intrinsic semiconductor. Directly you can substitute it. Okay, so this is the conduction in intrinsic semiconductor We have discussed how the conduction is happening place in intrinsic semiconductor, as well as you have to remember the values of silicon as well as germanium at room temperature. Okay, so if you want, you can note down this values that is present in the table. See, already Ne and NH, I have told you the formula. So see here, Ne, this is the formula. NH also the same formula will come here. Okay. Okay, so note down this formula, and the values that are present in this table also you should remember it, because they will confuse you only with this values. You don't know the value. If you don't know the value of mobility of silicon 0.14 and for holes it is 0.05, the answer will automatically go wrong. Okay, so remember this two different values. Next, that's all about the intrinsic semiconductor. Now in extrinsic semiconductor, one extra additional thing we will see. Remaining everything is same. One additional extra thing what we are going to see is, as I have already told you, it is a impure semiconductor. So it is differentiated into two different types. One is P type and the other one is N type semiconductor. Okay. So now in this point of view, for mathematical representation, what you have to remember is you have to check for doping. In intrinsic semiconductor, they will ask you the question which is related to mobility. But in extrinsic semiconductor, they will ask you the question which is related to the doping concentration of silicon. That's what we are going to see. Okay. So see here, this is your N type. The green color box represents your N type, and this pink color box represents your P type extrinsic semiconductor. See, we have used the Fermi level in intrinsic semiconductor. We have used the minimum energy level, which is represented by Eg, which is equal to 1 electron volt. But here a new term is coming into the picture, which is denoted by the ionization value. You can see here E ionization, which is approximately equal to 0.01 electron volt. So what is this particular ionization value? So you can see through the definition which I have given in the right hand side box, which is represented in the green color. Suppose if the electrons are not having sufficient energy to reach the conduction band, then automatically a donor level will be given, which is represented by Ed. This donor level will make the electron to move freely from N type to the conduction band that is present in the down part, which is represented by using 0.01 electron volts. And the condition which is given for ionization to take place is always the energy gap of ionization should be lesser than the energy gap, minimum energy gap, which is equal to 1 electron volt. Either it may be 0.5 or 0.8, not a problem, but it should not be equal to 1 electron volt, or it should not be greater than 1 electron volt. Okay, so this is very important case in terms of extrinsic semiconductor in case of silicon. Okay, next thing, in P type, see, remember two different words. In N type, we have used the donor level, which is called as Ed. But in P type, we are going to use the another term, which is called as EA, called as acceptor level. So what is the case here? Exactly opposite to N type. The ionization value should be greater than 1 electron volt. So you see here, you can see in this diagram, P type, what it is doing, what is the upper band here? It is equal to the conduction band, and the lowest band is equal to the valence band. Now the P type electrons are trying to merge with some of the holes that are present in the valence band, but sufficient energy levels are not provided. So therefore an acceptor level of 0.01 electron volt is automatically provided in terms of P type, and as a result the holes as well as the electrons are combined with each other. So remember, in extrinsic semiconductor doping, you have to remember two different words. For N type, it is donor level Ed, and for P type, it is acceptor level EA. Both are equal to 0.01 electron volts. But the condition here is for N type, EI should be less than EG. For P type, EI should be greater than EG. Okay. So now let us move to the problem. With this basic, we should see through some of the problems here. So first, let us see about this particular problem where direct representations are given. First, we will read the question here. Okay, we should understand the questions clearly first, then only we can able to solve all the problems. Because what I have already told you, you should remember whether what type of materials they have given, either it is equal to silicon or either it is equal to germanium. That we have to remember it, then only we can able to solve the problem. You can read the first problem here. Okay, I will read for you. So see here, silicon. First line itself they have mentioned clearly. They are going to use a material which is called a silicon, and as an additional advantage, they have given you the band gap also. You can see that the band gap of silicon is equal to 1.12 electron volt. What is the band gap here? Eg is equal to 1.12 electron volts. Okay, what is the next thing we have to observe here? Room temperature they have given, the value of T they have given here, and with the Fermi level located exactly in the middle of band gap. Again, I will go to the diagram. You can see the diagram of intrinsic semiconductor. See here, where is the energy band located here? Exactly at the mid. So this is the diagram for representation for this first question which I am showing here. Okay, so what now you have to find? You have to answer two different questions here. First, what is the probability that a state located at the bottom of the conduction band is filled? How many electrons are filled in the conduction band? Either 100% electrons are filled or only 90% of the electrons are filled. That we have to find it out. Next thing is, we have to find what is the probability that a state located at the top of the valence band is empty. How many electrons and holes are remaining empty in the valence band? That also we need to check here. Okay, so remember here, first thing is silicon is the material which we are going to use. Directly they have given the band gap, and they have given you a hint also. What they have given you the hint? They have told you to use the formula which is equal to Eg divided by 2. Okay, so you have to find the conduction band, how much it is filled, and in the valence band how much it is empty. These two things you have to just find it out. So already I have used the formula. Okay, so write on the formula first. Write on the formula first. What is the formula here? You will write the probability of expectation formula. Okay, so what is the probability of expectation formula here? P of E, right? P of E, I have already told you P of E. Here they have represented by using the Fermi function directly. That's why they have given here as F of E. It is your wish whether you can use P of E or you can use F of E. Okay, so F of E is equal to 1 divided by 1 plus E power E minus EF divided by KB into T. Okay, so now another hint they have given here. Identify it and tell me what hint they have given here. So you can see there, E is equal to EC. That's what they have given here. The reason is very simple. EC minus EF will give you the exact values as compared to E minus EF, because they have already told you the Fermi level is located exactly at the middle of the band gap. That's why here we are going to consider E is equal to EC. So directly substitute the formula here in the second step. You can see that F of EC is equal to 1 divided by 1 plus E power EC minus EF divided by KB into T. Now what you are going to do? You are going to separate the numerator and the denominator. That's why you are getting the exponential terms at the top. which is equal to e power minus ec minus ef divided by kb into t. Next, what we are going to do is we have found all the approximate values. Next thing what we are going to find, we have to find what is ec minus ef. That's what we are going to find here. And always remember that whenever they have given the hint like Fermi level is located exactly in the middle of the band gap, that means E is equal to Eg by 2, then you have to check the value of Ef first. Ef, okay, Fermi level, okay. So Ef is equal to Eg by 2, but what is the formula for Eg? Eg is equal to Ec plus Ev divided by 2. That's what they have substituted the formula directly here. Then after substituting the formula, from this itself they are directly finding ec minus ef. But what I have already told you, you can see through the formula, don't wait for substitution, okay, directly go for the formula eg by 2 because they have given you the question directly here. So don't put these equations and don't waste your time in your examination point of view, okay. So directly substitute the formula which is equal to eg by 2 and get the probability values here, okay. So eg already we know 1.12 electron volts, kb into t, substitute the k value, multiply it by 300k, you will be getting 0.026 electron volt. Already I have told you, no need to multiply with the k, you already know the value of silicon. That's why I have given in the introduction itself all the values I have represented in the slide. Again I will show you. So see here, k into t 0.026 electron volts. And if you want to use, if you don't want to use the formula Eg by 2, directly you can have the values as 0.55 electron volts. This is for your representation because this is a time saving manner, okay. In gate, what you have to remember, always I will tell you that you have to save your time, then only you can able to solve most of the complex problem. So you see here, it will take just only half second for you to solve this problem, but if you are making all these derivations like what they have given here, it will take you nearly 2 to 3 minutes exactly waste. That's why I have given the values directly here itself, okay. So if you didn't note down, please note it down in your notebook. The value for Eg by 2 in case of silicon is 0.55 and the value for K into T in the denominator is equal to 0.026 electrons. Okay, so directly substitute it and finally you will be getting the value of exponential value as minus 21.5. Substitute it and see. See, substitute. What you have to substitute here? 1 divided by 1 plus e power 1.12 minus ef into, sorry, divided by kb into t, 0.026 electron volts. Already I have told you, you can substitute directly as 0.55 instead of ec minus ef. So 1 divided by 1 plus e power 0.55 divided by 0.026, automatically you will be getting the values as 4.43 into 10 power minus 10. This indicates that a non-degradable semiconductor is obtained with respect to the conduction band as well as valence band. Okay. So very simple question. The basic question I have told you. Now what you have to do is, I will go to the next slide. We will look at the B part now. Okay. It's not moving. 1 minute. see here, we will go for the B part here. So again, see here, the Fermi level, again, the concentration is given by 1 divided by 1 plus e power e minus ef divided by kb into d. But what you have to take here? What is the B question they have asked here? Check here. What is the probability that a state located at the top of the valence band is empty? We have found only for conduction band, but we have to check how many electrons that is present in the valence band is empty. So see here, in this case, we have to make E is equal to EV, then we should proceed. But in the previous case, what we have did, E is equal to EC, conduction band, E is equal to EC, but here it is valence band, that's why E is equal to EV. The same formula, substitute it, use the direct case here. Already I have told you how to use the direct case. The same answer you will be getting here. That represents a non-degradable approximation is obtained in case of silicon as well as in terms of conduction as well as valence band. Okay, so now let us see through the next question. Again, they have given you the problem to be solved for the material which is called as silicon. They have not given any room temperature here. They have given you 5 different questions here. Okay, so let us solve these questions one by one. First one, read the question properly. For silicon at room temperature, what is the value of silicon at room temperature? We all know that the value of silicon at room temperature is 293. Okay, so now we have to calculate the following quantities. Density of states in conduction band. In the first question itself we have solved. Same we have to solve here, but they have given the energy level. Observe the energy level, 26 MeV they have given. What you have to do is convert it into electron volts. Then only you can able to solve the problem very easily, and you can able to solve it in a timely process. Okay. Second thing, the density of states in the valence band, E is equal to EV. Previous case, you can see through the previous first 1B which I have solved here. You can look at the top of the slide where I have solved here. The same thing you are going to solve for this B. Third thing, the effective density. Now this is your new quantity that you are going to measure. Effective density. Previous case we have calculated only the density of states, but in this case we have to find what is the exact effective density of conduction band, what is the exact effective density of valence band, and at last you have to compute the ratio of NC as well as NF. This is what you are going to do. Okay, is it clear? I will repeat again. See, the density of states we have calculated in the previous case. Okay, in the first diagram, in the first solution part which I have told you, there you can find the density of states, but here the value of energy they have represented directly. You have to use the approximations as E is equal to EC and E is equal to EV. Then you have to solve the problem. Next, you have to find new quantities. What are the new quantities here? What is the effective density of conduction band? What is the effective density of valence band? Then finally, you have to check what is the ratio between NC as well as NF. Okay. First, let us begin with the particular equation which is represented by the formula. When E is greater than EC, you will be having Mn into square root of 2Mn into E minus EC divided by pi square into H cube. Okay. See, I didn't tell you the equation in the introduction part. I will tell you another suggestion. First, let us see through what is the effective density. Then we will come back to the density of states. Okay. Because if you understand this basic formulation only, you can able to solve what is the number of density states that are present in the conduction band as well as in valence band. Okay. So now let us check here. You are having the formula for NC, which is equal to 2.5 into 10 power 19 into Mn divided by M naught power 3 by 2, which is represented in centimeter cube. Okay, this is how you have to find the effective density of states. The effective density of state is given by the direct formula here. Okay, we have to find the NC here, effective density. So the formula for finding the effective density is 2.510 into 10 power 19 into Mn divided by m naught power 3 by 2, which is represented in centimeter cube. They have given you the value of Mn also. Mn is 1.18 into m naught. So automatically m naught and m naught will be getting cancelled. 1.18 power 3 by 2 you have to calculate, and you have to multiply with 2.510 into 10 power 10. There you will be getting your effective density of states. Now you have found NC. Okay, now the same formula here, you have to find what is the effective density of the valence band. But here you can observe a small difference. There we have given Mn. Here in this formula 2C, you can able to see we have given the formula as Mn. We have substituted 1.18 m naught. But here in case of valence band we have given MP, and in this case Mn is equal to 0.81 into m naught. Automatically m naught and m naught will be getting cancelled. If you separate the numerator and denominator, automatically it will be cancelled. Then you will be getting the value of effective density states, and you can take this two different values, 3.62 as well as 2.06 into 10 to the power 19. So 3.62 divided by 2.06, you will be getting the percentage of effective states that is present between valence band and conduction band. See, this is very, very simple. Now, with this formula, you are going to find what is the density of states. Okay, for conduction band, how much it is filled, and for valence band, how much it is empty. That's what you are going to do now. In the previous case, that means in the first problem which I have solved, they have given you all directly. They have given you the energy band directly. They have given you the value of temperature directly. But see, in this question, they have not given you anything. They will ask you the question like this only. Okay, so for this type of problem, you have to remember the formula as for conduction band, the number of electrons that is already filled is equal to Mn into square root of 2Mn into E minus EC divided by pi square into H cube. This is the basic formula. But in order to solve in a timely process, directly go for the formula which is represented here as 1.05 into 10 to the power 56 into Mn divided by m naught power 3 by 2 into square root of E minus EC. See, this formula you have to remember. Two different formula. First one, probability of expectation. It is very, very simple. 1 divided by 1 plus E power E minus EF divided by K into T. That you can do it. This formula, you have to remember the values exactly. 1.05 into 10 to, because all these values are solved here. If you solve this during your gate examination, then automatically time will run for you for a single question. So what you have to do is you have to remember this formula for calculating the density of states. You have to find how much number of electrons are filled in the conduction band. Okay, so see here. Remember the formula, Gc of E is equal to 1.05 into 10 to the power 56 into Mn divided by m naught power 3 by 2 into square root of E minus EC. What you have to do now, just you have to calculate the value of E minus EC as well as Mn divided by m naught. See, already we know. Already I have told you in the C part as well as in D part, the value of Mn is equal to 1.18 into m naught. That's what they have substituted here. They have found the values as 1.35 into 10 to the power 56. Now we need to find what is the value of E minus EC. That's all. Directly you can put it. Okay, E minus EC it is equal to 0.026 into 1.6 into 10 to the power minus 19. So automatically you will be getting the value as 4.16 into 10 to the power minus 21. Just you have to multiply it, and finally you will be getting the value of Gc of E. This is how you have to find how many electrons are filled in the conduction band. Now next, same formula, but one additional thing what you are going to do is you have to multiply the value by using 2. That represents the number of electrons that is not filled in the valence band. I repeat again, the number of electrons that is not filled in the valence band, that is represented by using the formula Gv of E is equal to mp into square root of 2mp into Ev minus E divided by pi square into h cube. After solving all these formulas, you will be getting the final formula as Gv of E is equal to 1.05 into 10 to the power 56 into mp divided by m naught power 3 by 2 into square root of Ev minus E. Okay, what is the difference between the previous formula and this formula? Observe it clearly. It is E minus Ec, and now it is Ef minus E. Okay. Sorry, I have muted myself. Okay. So now let us continue with the same formula. Observe the difference in terms of formulations here. See, in conduction band, it is equal to E minus Ec, but in valence band, it is almost equal to Ef minus E. This is, sorry, Ev minus E. This is how you have to find the exact density of states that is present in the conduction band as well as in valence band. Okay, so automatically substitute the values directly here. We know the value of mp. Mp is equal to 0.81 into m naught. So m naught and m naught will be getting cancelled. You will multiply 1.05 into 10 to the power 56 with 0.81 multiplied by square root of Ev minus E. See, Ev minus E, E minus Ec, both will be having the same value, which is equal to 4.16 into 10 to the power minus 21. So don't waste your time. Exactly what you are getting for the conduction band is equal to the valence band only if the condition what they have given is if the energy gap lies in the midpoint of conduction as well as valence band. If this condition is satisfied, then you can use this particular formula like both values are equal. You can observe here 4.16 into 10 to the power minus 21. Previous case also, we got the value of E minus Ec as 4.16 into 10 to the power minus 21. So always remember, don't solve it separately. Find a common value for square root of E minus Ec and for square root of Ev minus E. Both are common. Take it and directly substitute it. But the only thing is the value of this mp divided by m naught is going to vary, because mp by m naught in the previous case we got as 1.35 into 10 to the power 56, but in this case you will be having 7.65 into 10 to the power 55. Only thing you need to check is what is the value of mp here. Okay, so this is your first problem. Whether they have given you directly, you can solve it easily. Mostly they will ask you in 1 mark question, but this second question they will ask you in part B. Okay, so either they won't give all these 5 questions, but at least they will give you 2 different questions for solving it. Okay, so next, just we will see this particular question alone. Then after that, the same thing what and all I have told you, you take it as a homework and you should solve it and you should show me in the next class. Okay, so you can copy the problem here. I will send you I will send you the question also. Okay, consider a region of silicon. Here also silicon material is used at room temperature. Room temperature is exactly equal to 300 Kelvin. For each of the following cases, you have to calculate what is the equilibrium condition in case of intrinsic semiconductor. That's what they have given. Okay, so you copy this question, you solve it in your home, Already I have told you what are all these formulas in the previous class itself. Just to take it directly. It is a direct substitution case. In the next class, I will show you the fourth problem, how to solve if the values are not given. Okay. So we will see in the next class. Okay. Thank you.